Well, thanks a lot for the kind introduction. I'm really happy to be here. It's such a beautiful place. For today's talk, we're in the mathematics department, but there's going to be very little math. That said, a lot of what I'm presenting is actually backed by a lot of math. And if you go and read some of the papers that I'm going to touch on, you're going to see a lot of math. But I want to simplify it so that I can cover a bit more breadth. And if you have any questions, interrupt me, let me know. I'll ask you some questions as I go to just cater to the interests of the audience. So what we're going to do is we're going to take a big picture overview of what's happening in the field of LLMs today, mostly from the lens of privacy. We're going to look at all the risks and how we can mitigate them and what are the sorts of technologies and algorithms and some of the underpinning foundations of those algorithms. So as Ganesh mentioned, there's going to be a lot of hypothesis testing, but it's really basic and really interesting and fun. So I hope you enjoy it. Before I go into the core privacy part of the talk, I'm going to try to tell you about something that I think is extremely interesting that has happened over the past, I would say, 5-ish years. And for those of you who are statisticians in the crowd, you will appreciate this. So a long time ago, I think 10 years ago in this field, 15 years ago, we were told that if you wanted to train machine learning models, what you needed to do is you needed to understand the application. You needed to model the application. Is it speech? Is it vision? Is it language? What kind of language? Is it English? Is it French? Is it Arabic? So on and so forth. And you needed to have the right architecture, the right model, the right statistical kind of patterns, the right data of that application, and you train one model per task. And we used to use very different models for vision, very different models for language. Remember, there was CNNs and LSTMs, and for speech models, all these different types of architectures. And in stats, we were told the curse of dimensionality is something extremely important. If you want to put in more stuff, you want to learn higher dimensional distributions, it's going to be very, very difficult. You need exponentially more samples in the dimensions in order to be able to learn that high dimensional distribution. So we were always told by our math profs and our stats profs not to go in the direction where we would make the problem harder and harder. And for some time it worked, and it worked well, for some applications at least. So AI was making its way into some applications until, I don't know who came up with this idea of saying, you know what, I'm just going to put it all together. I'm not going to listen to the mathematicians. I'm not going to listen to people who do distribution estimation. I'm just going to learn one model for all the tasks. And it seemed crazy for some time, and I still think it's crazy until today. How on earth are we combining all the modalities? Why is language related to vision and images and video and audio? It just doesn't make a lot of sense to train one foundation model that combines all these modalities, all these different languages. How is English related to, all sorts of Indian languages or Arabic or, all these things, or Hebrew or Persian? Like, this does not make much sense. They use different scripts. They use different structure. Why is even audio related to text and video? But it turns out that what we thought was a very, very high dimensional distribution is indeed something that lives in a much, much lower dimensional manifold. And by combining the data across all these modalities, we can better understand correlations and dependencies between all these different variables and modalities. So that ended up being very useful. And what we started seeing as we scaled the size of the models and the size of the training sets and the compute is this emergence of large foundation models. And this is a slide that I keep updating every couple of weeks, and it just keeps on getting outdated because the field is just moving really fast. And there's all different ways in which you can present this in terms of the size of these models, in terms of the scope of these models, in terms of the benchmarks they work on. You can look at it in many, many different ways, but the TLDR is that we are just moving really fast, and these models, no matter how much of a skeptic you are, I'm sure you've used them for one thing or another that you thought is really cool. Now, obviously, there's a lot of debate in our community whether or not we should be going in this direction, whether we should be continuing to scale the size of the models, the size of the data sets, or not, or we should specialize. But what has now become really kind of widely accepted is that we should start from a one base model that's very large, very powerful, and from that model, we should then extend it in order to specialize it on certain domains so that it could then become an expert in chatting or coding or applied to finance, applied to healthcare, applied to all sorts of different sectors. So we've turned the table around. Instead of starting specialized and then figuring out how to make the model a little more capable, we're now starting in the opposite direction. We start with something that's very general, very broad, and then we figure out how to specialize it and how to fine-tune it and how to improve it. And there are some people in the field today. I was just at iClear a few months ago, and a lot of people were convinced that what we can do with these models is just basically give them a prompt. This is one for healthcare, and we can see if that model by itself can do the research and can actually write the paper and give us the work done. I spoke to people at iClear, and they said that we're going to see this happen in about a year. We're just going to one prompt, one text, plug it through that foundation model, we would get the paper done. Now, obviously, it's laughable. And they say that because it has been trained on all of arXiv and all of PubMed and all sorts of research papers in the field, it's going to learn the patterns, what those papers are talking about, how they're structured, so on and so forth. And they think that that's enough. And that's, in my opinion, clearly not enough. It's impossible for us to just, based on training data from open web data, for us to be able to generate such a thing. But there's more reasonable people in the field that are saying, look, maybe what I just presented is not going to happen, is never going to happen. It's just not possible. Because how do you create new information out of nothing? But if we create some sort of an automated scientific method, maybe that can happen, or a form of it can happen. And so they're thinking of this loop where you start with a model that helps you create some hypotheses, come up with some interesting ideas to try. And maybe it's going to generate many, many hypotheses based on what it has seen from prior work and so on and so forth. So these are problem-specific hypotheses. And then you can take these hypotheses and you can create an experimental plan. You can create a plan that essentially tells you how to construct either a simulation or conduct a physical experiment in a wet lab of some sorts. So you take that experimental plan, and that's another model that specializes in creating those sorts of experimental plans, and you run that experiment. So you use either a Python, runtime, or you use robotics, or you're in a wet lab, so on and so forth. You run these experiments, you digitize their outputs if they're not digital, if they're analog, and then you verify the results. You verify if your hypothesis was correct. And again, there's a model there that's trying to analyze the outputs of these experiments, and it tries to tell you whether or not the results make sense, and you iterate. Maybe the first few hypotheses are completely off. You use some sort of reinforcement learning to try harder and try more, and hone in on the things that are working well and move away from the things that are not working well. And while this has not been done yet, no one has actually successfully used this loop at scale to solve open questions in healthcare or in other fields. It seems promising. This seems to be something that more people are willing to buy. More people are willing to kind of accept. And so you can see how we went from these tiny little models that are designed for one specific thing to something that can help us solve some of the big science problems. And it doesn't seem so crazy anymore. But, we can talk about lots of things. And in this school, there's going to be people who are going to tell us a lot about how to use these models for all sorts of things. In fact, the second speaker in this day is going to tell us more about how important these models are in biology and in healthcare and whatnot. So I'm not the expert in this field. I know very little to nothing. But what I know is that for these models, the ones that I am showing you on this figure, to be really good at doing this process, they need to actually be specialized on data that they have not seen in the pre-training. There's no way that from just data that we see on the web, open web data, we can get these models all to work well just right out of the box. And so that is the thing that I want to talk a lot about in this series of lectures. And it's basically a distribution shift problem. And this is very basic. So the blue distribution that you're seeing on this slide is the one that models the pre-training data set for all of these foundation models. And that's one thing that's actually quite common amongst all these big, large models. They're all trained on things like Wikipedia, news websites, blog posts, GitHub code, books and encyclopedia, research papers from arXiv and PubMed, all the open public research papers, so on and so forth. And they're powerful. There's already a lot of information in these sources of data. You can already do a lot because there's so many different languages, so many different modalities and applications. So you can get a very powerful model by just training on this blue distribution. But when you take them and you want to do something really cool, really interesting with them, you would actually need to do something that's very medical, let's say patient data related. And we just don't see on the web, in public, a lot of brain MRI scans. We don't see a lot of blood work because it's very sensitive. This is very personal information. You just can't put it out. No one can just open source all this information and just put it out on the web. You don't see biometric data or user location histories. You don't see things like chats from humans or how we use our phones, the clicks and swipes and combination of apps that we have on our phones, or calendars, or financial data, transactions and trading and whatnot. These are all locked internally to businesses and enterprises and on our phones and devices. And there's many trillions of tokens of data that are really high quality that we just do not access today. But it's going to be very important because, as you can see, this yellowish distribution is not exactly aligned with the blue distribution. These two are shifted apart. And we need to access this one if we want to do really well in practice. All right, so how do we do that? We can do it in one of two ways. Either we can take those foundation models and expose them to this data by further training. So this process is known as some sort of fine-tuning. You could do like soft fine-tuning or hard fine-tuning. There's all kinds of techniques and methods. Or what we can do is we can retrieve the relevant information at inference time. Once we've trained these models, we could bring in the relevant data for a specific application or domain, and we can present it to the model. We can tell the model, here's some data that I think it can help you solve this question. Look at it, explore it, use it. We can ask questions about the data, and we can give it at inference time. And the second part is something that's emerging. If you've used these models and if you've read papers about them, you may have heard of things like in-context learning, or it comes up in many different variety of names, zero-shot learning or few-shot learning, where you give the model a few examples. Like this is what the data looks like. This is what this task, an example of this task looks like. Here are some examples that I want you to learn from. And the large models, at least, are very capable at learning from their inputs. If you give them a few examples, they can learn the patterns of those examples because they're strong learners at their core. They just need a few examples, 2 to 3 examples, or 5 examples. And that's why this second approach is proving to be quite useful. But it's emerging, and there's a lot of work that needs to be done. So I'm going to focus less on it. In the first 2 parts of my lecture series, I'm going to focus on the first part. That's the bulk of my talks. And then towards the end, I'll tell you a lot about the last one, because there are many open questions that you might be interested in solving and working on. So how do we actually do the first part? Let's focus on just training these models. I argue there's a taxonomy of data that we need to keep in mind throughout this talk. We can start at the top with the public data sets. These are the things that we've already talked about, the Wikipedia or public domain data. And then as we go down this hierarchy of data sources, we start getting more and more specialized and personalized and more sensitive. So we go from fully public to semi-public. When we talk about semi-public, these are web scrapes, maybe forum posts, things that you've posted on Stack Overflow, things you've posted on Reddit, so on and so forth. You're answering questions. They're starting to be a bit more specific, but these are humans that have written very precise answers to very precise questions, or they've shared their opinions with the crowd. But then as you go even down, further down in this taxonomy, you get to centralized data. And think of these as basically your emails, your photos, your search history, anything that's still centralized in data center, but it's your data. It's not something that you would expect companies to train on, at least not their foundation models. But then you can go even one step below that, and we can talk about on-device user data. And this is like the really sensitive type of data source. So think about anything you type on your phone, the clicks and swipes, the location of your device, the speech. These are things that we don't even log, and we don't even store, we don't even put internally in the cloud. And I argue that with these different types of training data, some of them are, as we just saw, already being used to train these large models. So it's not a surprise that the first two, the blue ones, are already being used to train these large foundation models. These are multimodal, very large, hundreds if not trillions of parameters, trained on tens of trillions of tokens, so on and so forth. They live in the data center. There's no way you can serve them on the phone or on your laptop. So they're really large. They need a lot of resources, not just to train, but to also do the inference part. But as we start, specializing these models, through reinforcement learning, we're already using some of the data sources that are, below in the taxonomy. So like when you interact with a lot of these models, whether it's Gemini or ChatGPT or whatever model you use, you're giving it information about yourself. You're asking it questions. A lot of us are today, for instance, if we have any sorts of symptoms, we go to that model and we start analyzing our symptoms and we start iterating. If we're feeling down, a lot of people are actually using those models as some sorts of a personal therapist. And so you're putting and plugging in a lot of your personal information. These are logged and stored in chats, and they are then used through reinforcement learning to make that model much better at conversations and all sorts of topics. So we already are doing this instruction tuning and continuous RL to improve the models on sensitive information. That's one way in which we're starting to incorporate these personal data sources of information. But the other way that we've seen this pan out is we're starting to distill these models to smaller models. And these are, think, 1 to 10 billion parameters. They're still large enough, but now they're specialized. Now they are, more a model for finance, a model for healthcare, a model for, all sorts of like a personal assistant. And this is something that could be served in the data center, but it could also be served partially on your computer, laptop, or personal device. And so we use this process of distillation to go more task specific. And for that, what we do is we do some process of fine-tuning these models on potentially sensitive data. It's client data, enterprise data, user data, so on and so forth. But what we're trying to work towards is something that we like to call per-user models. Each person would have their own model. And so these are highly specialized, or personalized if you want. They're much, much smaller. They're expected to be less than 1 billion parameters. They are fully stored on your device, so either your laptop or your phone, and they are your model. Each one of them belongs to one individual human being. And so these models are expected to be largely trained on the two data sources that are extremely sensitive. And there's this process of personalization and making the model work really well for one individual. So they should know your tone, your style, your behavior, your patterns, the languages you use, the habits that you have, the people you interact with, so on and so forth. And that is itself a big, big open challenge. How do you do it? How do you take something that was trained to work well for a lot of people and you make it work really well for one individual person? So I'm going to pause here because this is a very dense slide. I'm just going to emphasize one thing, that maybe we've solved some parts of this picture. Maybe the foundation model is the one that's getting a lot of attention and love in our industry and even our community. And we're moving very fast and making these models very powerful. But really, I think a lot of the value that you and I will feel is going to come from the distilled models and or the personalized per user models. And we haven't solved those pieces yet. Those are still open problems in the field. How do you best distill? What's the smallest model that works really well for one application so that we can serve it at scale? What is the best way to personalize a model at the smallest scale possible so that we can store it on device and serve it to billions of people? Because energy efficiency is so important, compute and storage and memory, all of these are going to be critical. Those pieces are still largely open problems. Even if you are just like a stats, ML, AI person and you just want to advance the field, a lot of the attention is going to be in these two areas. And likewise, because these models will touch sensitive data, a lot of the privacy problems are starting to emerge very, very widely. And so that's what we're going to focus on. But I'm going to give you an example of the type of data that we're starting to look at and tap on. So this is mostly on-device user data. And a lot of it is, basically, your daily lifestyle and routines. So there's a lot of it like commute times and the routes you take, the locations that you visit, your home, your work, your gym, chats and clicks and swipes, neighborhood demographics, travel habits, frequency, destinations, a lot of it. I mean, I can go through the list. It's a long list of very, very important yet sensitive information that these models could benefit from for them to become really better for you. Now, obviously, this is sensitive. I wouldn't want anyone to just train these foundation models directly on this data and for them to be able to potentially memorize this data. So we need to treat it with a lot of care. And that's why we need more than 3 hours to talk about all the sorts of things that can go wrong and how we can fix them. And that's going to be essentially the topic of my lectures. So one way to do this is to actually not collect this data and not store it and centralize it in one place, but try to actually keep it where it is on your device and see if we could train on it or leverage it in some way to improve the model while the data stays where it lives or where it was born. And so this was the core idea behind decentralized learning, federated learning, so on and so forth. And I'm just going to overview it very quickly. You may have seen it. It's actually quite simple. The way it works is you start from a model that's pre-trained. Again, we're in this era of we pre-train these models on web data, on open source data, and we use that as a strong initializer, and then we try to specialize it. We try to personalize it. And so what you do is you have the server share the model with a select subset of the devices. So they each get a copy of that model, and we try to locally on device update this model on the local data. So we use whatever machine learning runtime we can run on device. Maybe it's PyTorch, maybe it's JAX-based, whatever machine learning runtime you can run on phones to update these models. And once you have an updated version of each model, we can run a few steps of stochastic gradient descent, keep it cheap and simple. You could then take these updates and send them back to the server, aggregate those updates and use that aggregate in order to update the pre-trained model that we started with. And obviously, this process can be repeated many, many times so that we capture a large number of users, maybe a good fraction of the users. And the hope is that this thing alone is going to give you much, much better models. And hopefully, it's not going to leak a lot about users. That's the hope. And this thing, when it came out and Google used it extensively, it became quickly very popular. I'm just going to give you a few examples of places in which we use this idea. You can see that it's used in Google Health Studies. This was very important in the pandemic era to try to understand, how diseases flow in communities. It's used in Google Maps. There's an application called the Environmental Insights Explorer that tries to understand mobility of the users, where they go to, what are the areas that have a lot of activity, so on and so forth. And this is with the hope of understanding mobility patterns in order to reduce carbon emissions. So it's serving a very good cause. We use it in Android devices to do the smart text selection. We use it in the Google keyboard to do next word prediction, grammar checking, spell checking, so on and so forth. And we use it for the hot word detection in the Google Assistant. So it's used in a lot of places. I mean, this is also just a sample of use cases at Google. It's actually used across the industry. It's used by Apple, it's used by Facebook. A lot of companies are developing it, improving it. So it's not just Google. So it's important. But why did it catch a lot of people's attention? It did because it gave this impression of being able to improve the Pareto frontier of the trade-off between privacy and utility. It said, look, this data was locked. And we couldn't access it. We couldn't train on it due to these privacy concerns. And so our utility versus privacy trade-off curve was either you want to let go of privacy and get a lot of utility, or if you wanted privacy, you would get no utility whatsoever. It was like an L shape. Either you get high privacy, no utility, or you get very low privacy and then high utility. And what this technology essentially did is it said, no, actually trade-off shouldn't be that bad. There should be a better way of tapping on this data without centralizing it, without vacuuming all the data and putting it in one place and accessing this data. We should be able to still learn from it, these patterns that are common across a lot of devices. And that's why it essentially gave us this impression that we can improve the Pareto frontier, and that's why it became so popular. And it turns out that really what it's trying to do, what federated learning or decentralized learning is trying to do, it's trying to encode this privacy principle that's called data minimization. So if you look at the different stages of training in this decentralized learning approach, what's happening is that we're trying to reduce the amount of information as we move left to right. So there's minimized data exposure because we're focusing on this one specific domain of data that we're training on, whether it's in the Google keyboard or in the Android smart text selection or in the Google Maps application. We're not just putting things all together. So there's minimized data exposure. And there's focused updates. When we only send the updates that are necessary for a specific ML task. And then we aggregate them immediately. We delete all these gradients that came from devices, the model updates that we got across devices. So they don't get logged and stored forever on data centers. And when we train across days and weeks, we don't log and store all the checkpoints. We just deploy the final model. So as we go from left to right, we're trying to minimize the information as much as possible. And this is a good practice. I argue that this is important. This is necessary to reduce the surface of attack, reduce the amount of things that can and will go wrong, make sure that less engineers can access very sensitive information, and just have one model that works really well for a variety of users that we can then take and personalize. So this is the data minimization principle, but the issue is that the data minimization principle on its own is not enough to solve all the privacy problems. It's just not enough, yes.
If I understand correctly, what you are essentially trying to say is from the device to the server, you want to minimize the amount of data sent, and from the server to the engineer, you further want to minimize it?
Correct.
Oh,
And from the engineer to deployment, you also want to further minimize it. Because what gets deployed on devices, so how many engineers do you have on the, let's say, Google keyboard team? Maybe tens, hundreds, let's say, of engineers. So the amount of exposure you have is on the order of 10 to 100 people. You want to make sure that those people are trustworthy. But when you take that model and you ship it to the phone and you use it on device, then you have billions of phones. If one of these devices is hacked, or they didn't do the software upgrade, they didn't patch whatever security loopholes were known, suddenly the model is out and anyone can access it. It's in the public. So the surface of attack is growing as we move left to right. And so what we're trying to do is we're trying to reduce the amount of information that's exposed to the more actors that can access it. All right, but this alone is not enough, and that's actually the main point of this talk. There are other principles that we need to respect in order to get a holistic picture of privacy, and in order for us to actually figure out how to solve all the things that can and will go wrong. So this is not even comprehensive. If you go talk to different people in the field, they'll tell you different things. This is essentially my colleagues and my take on this. We think there are four main principles for privacy. The first one is transparency, auditability, and control. And what it means is that, first and foremost, the users of these applications should know whether or not their data is being used to improve the services. They should be able to consent. They should be able to opt out or opt in. If they are okay with it, they can say, yes, I'm okay with it. And if they're not okay with it, they should be able to say, no, I don't want you to use my data to improve this service. So we should be transparent about where and when we are using this data. And we should give the user the ability to actually control where their data is being used. And then there's the data minimization principle. That's the one that we just talked about, the one where we try to minimize the data as quickly as possible by restricting access, by doing focused collection, by using encryption. Everything is end-to-end encrypted so that nobody on the wire can actually tap and listen, so on and so forth. The data should be deleted if it's not needed anymore. It should be short-lived, etc. And then there's one that's actually quite important, which we call data anonymization. If you've seen regulations like GDPR, it talks about anonymization. What it means is that whatever computation that we run on the data, whether it's a simple statistical query or whether it's we're training a model on the data, a generative model or a discriminative model, the output of that model should not reveal anything sensitive about any particular individual. So the released outputs from those models and those computations more generally should be somewhat anonymous. They should not be traceable to any individual. And there are technologies that we're going to talk about, like differential privacy and others, that serve this principle. And finally, there's the principle of we need to be able to verify what these companies are doing. So if somebody tells me, look, I'm using a combination of federated learning, encryption, and differential privacy to train my models, are they really doing that? What type of encryption scheme are they using? What type of differential privacy scheme are they using? What type of noise? How much of it? Where are they adding this noise? Can we verify all these steps? Can we audit and make sure that they are indeed applying the things that they claim to be applying? And so this is another principle that is important. It should be ideally applied by the users themselves or at least by external auditors. So today I'm going to focus on these two. We've already talked about data minimization, so I'll switch a little towards data anonymization, and then I'll talk about the combo of the two, how they work in tandem together to give you a really comprehensive solution. And then tomorrow I'll talk a little bit about verifiability, auditability, and some transparency and controls. All right. So let's talk about the main issue here and why federated learning is not enough. At least the version that I just presented to you, the vanilla, simple, decentralized learning one. The issue is as you scale these models, especially the generative models, you start getting into a regime where these models are just capable of memorizing some of their training data. So I have a group of colleagues at Google in the privacy and security team. They specialize in essentially attacking models and poking the models and trying to see what they have learned. Very clever people. And what they've done over the past couple of years is that they've taken all these models from GPT-2 to Stable Diffusion to ChatGPT and others. And what they were able to demonstrate is that across a variety of these foundation models, you can poke it in a way. Sometimes it's very weird. It's like what you put into the model and the prompt is something that you would have not expected. But then you can extract from these models training data. And you can see that in a lot of cases, the data that's extracted isn't just any training data, isn't common patterns and patterns that you would expect these models to produce, like saying happy birthday, or a national anthem of a country, so on and so forth. No, it's actually personal data. So you can see, and a lot of it is redacted intentionally, someone's email, someone's name and phone number, physical address, so on and so forth, someone's image. Granted, this person is a public person, so it's not a violation of privacy. And by the way, all this information is actually on the web because these models are trained from web data. So none of this is a violation of privacy in some sense because these people have put out their information on the web. So you can look it up, you can Google it, you can find it. But it just is a demonstration of the capability of these models to retain sensitive information and regurgitate it. At inference time, if you prompt it cleverly, you can extract out some of this information that it has seen at training time. And it is because of this that decentralized learning on its own is not enough. Because sure, you've kept the data on device, and you've trained these models in this very complex, distributed, federated way, but maybe the model that you've trained at the end of the day is capable of reproducing the information that it has seen during training, regardless of how you did the training. Even if the company does not have access to this information because it has not centralized it, it has not logged it and stored it, because it has access to the model that was trained, maybe it could poke the model and potentially reproduce that information. So this is quite important, and we've seen it across different applications.
A question?
Yep.
Is there like a tension here? Because what I hear is that you're supposed to train neural networks on the training data down to zero loss essentially on the training
Yep.
data. So is there a compromise if you don't do this in terms of, is there a trade-off there
Yep.
potentially?
There is actually a trade-off,
Yeah.
and this talk is going to be mostly about how do we explore the trade-off, understand the trade-off, and improve that trade-off. But yes, there is a trade-off. There's tension between privacy and learning, and I'm going to try to start working towards understanding that tension and trade-off. And actually, towards this point, we need to understand two concepts that are actually quite important. The first one is generalization. This is something you'll learn a lot if you take an optimization class, if you take any sort of stats learning, class. We talk a lot about generalization, being able to generalize to unseen data, because you have samples from a distribution, and you train your models on those samples, and maybe you see unseen samples and you want to do well on them. So you may have seen something called the generalization error of a model, so on and so forth. That's exactly it. But this is something we really want the model to be able to do. These are patterns that are common across many users or across many applications and individuals and so on and so forth. For instance, if I go to my keyboard and I type "what have you," it's kind of nice for it to be able to complete it with "been up to," because that's actually a common pattern. That's something that a lot of people use. There's nothing sensitive about it. There's nothing unique about it. It's something that you see very often in the wild. So that's generalization. It's simple. It's easy. It's good behavior, essentially. That's why it's green. But then there's something that we like to call privacy violation, and in the community, some people refer to it as memorization, as memorizing some unique training example. And this is very different. This is one where, if I go to my keyboard and I type Alice's credit card number is, and if it produces a credit card number that's valid and that belongs to Alice, there's a problem there. There's a big problem there. And memorization or privacy violation is when we have models that are so good that they can actually memorize certain patterns that only belong to one user. Because I don't expect to see Alice's credit card number on, other people's phones. There are very, very few entities, maybe only one entity that has that credit card number. Otherwise, they should be encrypted and locked. If Alice is using her credit card to purchase things, so on and so forth. So it should only be typed on Alice's phone, and it should not be typed on my or your phones, and therefore it's not a pattern that you would expect to see on many people's devices. It's just a pattern that you see on one person's device. And if the model can actually produce that pattern, it means that that model is, privacy violating. It's doing something that it's not supposed to do. It's not a good generalization capability. And that's the idea. And when Neil asked the question about, is there a tension here? Yes, there is a tension, because the better these models are, the higher the capacity they have. Whether you want to look at it as some, VC dimension, or whatever it is, however you define capacity of a model, number of parameters, so on and so forth, the more we train them, and the better they become, the more we have this type of a behavior. And sometimes we need this behavior for better generalization. So the thing that was a bit of a surprise to us is that we thought that if you just want to generalize, you can get rid of all the memorization type behavior. But it turned out, and there are countless of examples, even some that are theoretically grounded, where in order to generalize better, you need to memorize. If you don't memorize, you can't generalize. It's weird, but yes, we drive the training loss down to 0 on the data set, which means that, in theory, we've learned all the examples of our training set, each and every single one of them. So what we're going to talk about is essentially, how do we think about privacy? And what are the sorts of threats that we're going to have to resolve? And we're going to start simple, what I like to call as reconstruction attacks. And you may have seen these in the community as data completion attacks or memorization attacks. They come under all sorts of names, but it's actually quite simple. And so what this is about is, say you have a training set, and in this training set you have Bob, Carol, and Dave. And let's say we added a user, Alice, and Alice's data is of the form, Alice's credit card number is whatever. And we go and train a model. So we get the output after training. And training could be done however you want. Use the fanciest optimization algorithm you want. There's Adagrad and Adam and all sorts of adaptive algorithms that people use for these LLMs with all sorts of adaptation of learning rates, so on and so forth. So you get this model. It's a generative model for this talk. We're talking about mostly LLMs, but whatever you want. And then if you plug in Alice's credit card number is, you can do it many, many times. You can poke the model many times with Alice's credit card number is, and you want to see how often it's capable of producing the real number. So this is a very basic way of testing to what extent the model is capable of memorizing a person's data. Now, you have to be careful when you do this test. Here's why. What if in this user, Alice, instead of Alice's credit card number is blah, what if you have something like, please let me know if you have any questions, which is a very common phrase. Now, this one, even though Alice has it, we expect that many other users, in this case Bob and Carol, to have it as well. It's not unique just to Alice. And so in this case, if we plug into the model, please let me know if you, And if the model is actually with high certainty capable of completing the sequence, have any questions, then we shouldn't use this as a proof that there's any privacy violation. Again, this is a generalization behavior. This is not a privacy violation. Why? It's because it's common across all other users. So this is all to say that when we conduct these types of audits on the model, we have to be careful about how we do these audits. We don't want to get ourselves into these patterns that are common. And let me tell you why it gets very tricky. Let's use this example. So here I have a data set where Bob has a pet dog, Carol has a pet cat, maybe Dave has a pet bird, Alice has a pet cat. Let's say I plug into the model, Alice has a pet, and then it completes it with a cat. Is this a privacy violation or not? Who wants to guess?
Is it personal? Like, is it not dependent, like, shouldn't you ask Alice?
So this is a tricky one. A lot of people would look at it and be like, wait a second, you just discovered that Alice has a pet cat. So you knew Alice's pet, you knew that Alice has a cat. You just learned something about Alice. It's personal, right? It seems like a privacy violation. But I argue that it's not. It's one of those very tricky things. And the reason why it's not, I don't know if you've noticed, in this data set, cat is more popular than other pets. Of course, this is a toy data set, so it's very small. But I have 2 cats, but I only have 1 dog and 1 bird. And so the model has learned that there's more people with cats than people with other types of pets. And it's just producing cat because it's the more popular pet. So this is a tricky example of where, sure, you've learned something about Alice, but it's not because Alice has this unique property. It's because this property is popular in the data set. So that's also one of those things that you need to be careful about when you conduct these attacks. It might seem like a privacy violation, but it's maybe not a privacy violation. Now, I argue we need to be careful because it's weird. So like, even if this is a common thing, it might for the user, if Alice goes to this generative model and plugs Alice has a pet and it comes out cat, she would feel awkward about it. Like, how does the model know that I have a cat, So we have to be careful about how we serve these models, how we interpret their outputs. But that's a different problem. That's not really a privacy violation. That's interpretability and trust and how we communicate the behavior of these models. I think there was a question.
So if you did an experiment where you did this prompt after training Alice as a pet cat, you then did the prompt with lots of different people's names and worked out the average amount of times it says cat, and then you did it a load of times with just Alice's name and it says cat more often than the average, would you then consider that a privacy violation?
Yes, and that's a good point. So actually, this brings me to the next slide. In order for us to do these attacks properly, we need what we call a held out set. And this is, if you do stats and if you do learning theory, you've seen it a lot. How do you actually test generalization versus something like memorization? You need a held out set. You need to measure performance on something that has the same distribution but was not used in training. So in this case, for instance, we have Bob, Carol, Dave, and Alice. But maybe we have Eve as, like this held out user. I argue we would need more than just one data point. Of course, the held out set has to have a reasonable amount of users, a reasonable amount of samples. But, for the sake of just simple discussion, let's assume that, we have one user in the data set that we're focusing on and one user that's not in the training set that we're focusing on. And so what we need to do ideally, as someone just mentioned, is we need to measure the performance of the model on held-in users versus held-out users. If the model is capable of completing these sequences just as well on the held-in versus the held-out, then this is a generalization capability. It means that it's just learning patterns that are generalizable. There's nothing very unique to the training data because it's doing really well on held-out data. So these are patterns that are popular, so on and so forth. Whereas if the model does extremely well on the held in, but poorly on the held out, there's big discrepancy between these two sets, then we have to be careful. It means that it was overtrained, that it has memorized, that it has overfitted the held in data set. And that's where privacy violation can kick in.
Quick question about this. The query that we're making from the model side is Alice, in the previous one, Alice has a. If we're making from the model side, and it could be anybody's, can't we just cut that query so that it cannot be answered? Because Alice is private info, so any response to that would be a privacy violation. And only if it was a more general thing, such as a person has a pet, then it would be allowed to be answered.
So that's a good point. What we're doing here is we're intentionally plugging in this sensitive information into the model in order to test to what extent it has memorized. So think of these attacks as actually tests we're conducting on the model. So we intentionally want to plug in names of people so that we kind of like poke the model, hey, you've seen Alice during training, right? What did you learn about Alice? Do you know that Alice has a pet? What kind of a pet does it have? You know, so it's all being intentionally done here. But of course, in general, you know, when we launch these models, people should hopefully not be, you know, capable of knowing whose training data was in, and you know, to plug in names of people and so on and so forth. So yes.
Sorry.
Yeah.
So if he's asking that if in the first phase we put a placeholder instead of Alice,
Yeah.
or the model treats the names as placeholders, so there won't be any.
Right, but that doesn't mean so. If you're gonna mask the name of the individual, that does not mean that the model may have not learned that information. So the model could have still internalized that Alice has a cat. Now, if you never look for it, if you always mask the input, then sure, you're not going to activate that path in the model. But that doesn't mean that that path isn't already encoded in the model. And what we're doing here was we're intentionally trying to figure out whether or not those paths exist in the model. And that's why we're trying to activate those paths intentionally. That's the whole point, yes. In practice, you might want to do something like this. You know, when I launch a chatbot, maybe under the hood I need to mask certain things, yes. And you know, like anything that's not relevant, you know, I'll try to mask it, and people do that. You filter the prompts, you process the prompts, and then you plug it into the model, sure. But as an engineer who's developing these models, I want to try to understand to what extent there's these paths in the model. So that's just a technique for me to audit models. Yeah.
So I want to connect to one of your earlier slides.
Yep.
Let's say here you're basically saying you're improving privacy if you are generalizing.
Yep.
But I'm trying to understand if that also creates a tension between generalization or privacy improvement and personalization, which is also one of the goals in your previous slides.
Yep. So these models for now are models that should work well for a large number of people. I haven't gotten to the point where you're personalizing yet. For now, we want models that work for a large population of users. Potentially specialized for an application, but they should still work well for all the users. That's why we're training them on a bunch of users, not just one user's data alone. All right. Yep.
So one thing that kind of strikes me here is that you could have these multimodal distributions where as you increase the, I guess, the number of things that you know about Alice and Dave and Carol and Bob, you could start matching that, you know, like Alice does yoga and so does Dave, and therefore this has a, you know,
right.
their dimensionality is more similar.
Exactly.
Is there any work done in understanding how that, like how far in that matching dimension you need to go before it's you start running into this? Is it generalization, or am I violating privacy?
So that's a very good question. I'm not aware of a research paper that looks at similarity, but I'll tell you something that the community has done in a bit that's close enough to this, which is how many times you need to repeat some information in the data set so that it memorizes it. So I'll get to it, but it's not exactly what we're doing, because like data could be repeated, but not exactly. Like it could be near duplicated. There could be similarities, but not exact copies of it. And so the community has studied some of these questions, like near duplicates and similar patterns, but not exact patterns. And you know, how many of those do you need to have in order for the model to internalize it? As a function of the capacity of the model, how much you train the model. Yeah, and we're going to touch a little bit on it, but there's you know, a lot of work.
That felt like a bit of a gray zone there where you kind of, it'd be hard to tell which one's which.
Yeah, exactly. Yeah, maybe one more question, Sid?
This is sort of a dystopian question, but if the model can distinguish between a reconstruction attack question and a quote-unquote normal question and deliberately mask its output, like basically, what guarantees are there that this sort of a schema can, because on the one hand, you're driving it towards, training error 0, right?
Yeah.
So it will want not to forget in some sense.
Yeah. Absolutely, and there are people in the community who are less of a privacy purists that say, you kind of want the model to learn everything, it's fine. Let it learn everybody's information, all the nitty-gritty details of each and every single individual human being. If it's such a great model, and if it has learned and internalized everything, and it could also learn when the prompt is sneaky, and it can block the output, it's fine. Why are you worried? But then what if the model leaks out? What if the parameters of the model, get in the hands of the wrong people, the wrong entities? What if the service provider can go in and remove that layer of discovering, for instance, the content of the prompt and starts learning about individual users and maybe using that to sell their personal data or target them with all sorts of ads that they never wanted, so on and so forth. So, ideally what you want is not to have that information present in these types of models. But I agree with you that there are people that believe in that. In fact, well-meaning privacy engineers are trying to see if they could use some sort of reinforcement learning to teach the model to distinguish between these types of prompts. And similar to the question that was asked before, can we maybe mask the prompt? Can we transform the prompt? We know this information, but let's not reveal it, let's not release it. And maybe there's some application for those, but if we really want to be privacy purists, we ideally don't want the model to have it. So that's where the tension arises. Let me give you another potentially interesting result here. So these are experiments we've conducted on production models. Think Gemini models. In these Gemini models, we didn't work on the largest models, we worked on the smaller models. So about 27 billion parameters, so it's not super duper duper large, but it's very large. What we took is we took the data set with a lot of users, and we first did a random split of the data set. In this case, it's 6 versus 6, but in reality, the data set was split in a very unequal fashion. So you take just a small fraction of the users, and then the rest are what you train on. You take the upper split, and you split it into 2 sets. You split it into a held out set and a held in set. So there are users, the red ones, we're never going to train on those users. And the green ones are ones that we're going to train on. So what we're going to do is we're going to combine the bottom set with the held-in set. And we're going to take a pre-trained model. In this case, it's a Gemini, one of the smaller Gemini models. We're going to fine-tune it on this user data. Okay? So it's fine-tuned on both this bottom split and the held-in data set, the held-in users. But it's not fine-tuned, it's not trained on the held-out users. And what we've done is, for the held-in and held-out users, we've capped their number of training examples to 39 examples each. So each user is expected to have a lot of training examples. In this case, it's conversations. That's, again, a production use case. And we cap the number of examples per user to 39. This is, again, a method of minimizing the data. We don't want one user to have thousands of conversations, whereas the other only has 30 or 40 examples. Then it would be very imbalanced. Okay?
Sorry, what's the purpose of doing a random split before splitting into a held-out and held-in set here?
That's a good question. We wanted to make sure that it's representative of the training data. It's a natural IID split. And we want to make sure the held in and held out have also IID distributions. That's why it's like a random split of some sorts.
But then you can just do some random split into held out and held in sets.
Right, right. So you could have done the random split here at this point to ensure that these two are IID. But we want to model the risks, not that are particular to one demographic of user. We don't want to take only the English speakers, let's say, and do held in and held out amongst English speakers. We wanted to take a random sample of users, so that captures all sorts of, let's say, languages in this example. It's just a random slice and capture the leakage, the privacy leakage amongst this average demographic. You could slice it in an adversarial way. You could say, I want to pick one specific demographic of users from the data set. That's totally fine. This is not the only way of doing it. And I'm going to show you one way of doing it that's even better in a bit. 5 minutes? Okay. All right, so here.
Can I just ask where the magic number comes from?
39?
Yeah.
There is a reason, but you'll see it in the next talk. There is a reason. Why 39? I know it's, yeah. All right, so here's what we saw. If you try to reconstruct their strings, you could say I want perfect reconstruction. So at a distance of 0, that means that perfect match. You plug in a prefix. You see how well you can reconstruct the suffix. In this case, the suffix length is 10 tokens. The prefix length is 50 tokens. And you can see that, between the held in and held out. So on this one, uninserted is the held out. The inserted is the held in. So I changed colors. And you can see that at all these different distances, so it could be perfect reconstruction or approximate reconstruction up to, say, about 5 tokens at a distance of 5. You can see that the rates are high and statistically distinguishable. So they're not close enough between the inserted and uninserted for me to claim that the performance between held in and held out is exactly the same. You can see there's a bit of a bump. You can see it even with the naked eye between the inserted versus uninserted. And obviously, the inserted ones are memorized. We can reconstruct them more than the uninserted ones. So that means that these models are actually memorizing quite a bit of these unique training examples over users. It gets worse and worse if we do approximate reconstruction, not perfect reconstruction, but it's quite a bit. Now, here's how we can make the situation much, much worse than it already is, and this is interesting. What if we take users, and in this case, instead of taking natural users with natural data, like actual training data, what if we were a little adversarial? What if we plug in users with artificial data, random data? So in this case, the training sequence that I'm going to use is just a random sequence of tokens. You can see like it doesn't have any meaning. It's actually a combination of all sorts of languages. So it's just generated it by randomly drawing tokens from the vocab of the model. And I'm still conducting the same type of attack. I'll plug in a prefix into the model. I'll try to see to what extent the model can produce the suffix of that sequence. So it's the exact same attack. It's just now the data is more, it's weirder, essentially. So what I'm going to do is I'm going to do both types of attacks. I'm going to do the natural reconstruction attacks of training data, the way exactly that I showed you before, that split and then held in and held out with natural users and natural data. And I'm going to add the random stuff that I just talked about. So I'm going to have a bunch of fake users. Each one has 39, again, weird number, of these sequences that are generated at random. And what I'll do is for each user, I'll generate one random sequence, and I'll duplicate it 39 times. So each user would have the exact same training sequence duplicated 39 times. I want to make it really strong in many ways, like really adversarial. Now, notice there's no held out random canary users, and that's intentional because these canary users are random. We don't expect the model to be able to reconstruct these kinds of sequences if it doesn't see them. So we don't need a held out for reconstruction here. Now look at this. I'm comparing natural to adversarial. Adversarial is the random stuff. Natural is what I showed you 2 slides ago. Remember, for perfect reconstruction, the performance was about 1%, a little over 1%.